So welcome to the seminar today, and our speaker today is Harold Arma, who of course has many friends in India. He has been in India several times, and he's going to tell us about his new work on the tensor, in the correspondence of between neural networks and quantum field theory and applications of non-perturbative renormalization group in this context. So over to Harold.
Thanks a lot, Ayan, for the introduction and also for having me here. So yes, indeed, like it's in general, I try to come to India every 2 years, and it will be 2 years that I could not come because of the pandemic. So let's say that it's kind of my every 2 year visit. So thanks a lot for that. So today I want to speak a bit on non-perturbative renormalization for the NN-QFT correspondence, which is a work in collaboration with Vincent Laroche in CEA in France and Dean in the University of Abomey-Calavi in Benin. So I will start with some general motivations about why we want to do this and like where we are going. Then I will describe the NN-QFT correspondence by itself, and then I will explain how we can set up the renormalization group, and finally propose some conclusion. So why do we care about neural networks? So you have a theorem, I mean, in fact, a whole series of theorems which apply in various circumstances, but basically they all say that under some assumptions, a feed-forward neural networks F with a finite number of neurons can approximate any continuous function big F on a compact subset of Rn. So it's an existence proof, so it's not constructive, so it's not very helpful for practical purposes. But it's kind of already telling you that whatever your task to find some function to describe something, you should be able to use the neural networks to represent it. So it's very powerful theorem, and so it's why like people were very interested. But first, we were lacking computational power to really use them, and then recently, since 10 years, as most of you know, certainly, this has started to really start because we have more data and more like better computers. So what is a neural network, which I called NN in this talk? So it's a sequence of matrix multiplication and translations, which are the parameters we can learn, and nonlinear function, which are fixed. So in a sense, so if you just add matrix multiplication and translations, it would just be a linear regression at the end. So you need to add some nonlinearity, which you apply with function after each matrix multiplication. So in this way, you can get a function which is very complicated. But the idea is that to not have too many things to learn, because like it's hard to learn a nonlinear function because you are like, in principle, a function is represented by an infinite number of parameters. You'd say, okay, I will just learn the parameters for my matrix multiplication and translation, which is a more manageable number. And what's fantastic is that even with just this recipe, you can like validate this theorem. And what's even more interesting is that, in fact, by nonlinear function, you just need really like a discontinuity in your function. So one of the most used function is just 0 for negative parameters and x, so linear for x bigger than 0. So it's like a linear function, but piecewise. So most of the time what you do, so you do supervised learning. So the idea is that you give a set of pairs x and y, which is the result of your function, for example, as you measured somewhere in the world. And then you tune the parameters of the multiplication and translation with gradient descent so that your neural networks is approximating your function. So I will not enter in the details of learning today because there will be like no training during my talk, so no learning. I will just work with pure initialized network. But it's good to keep in mind that the goal at the end is really to do learning to get this task here done. So what are the motivations for neural networks beyond this theorem? So generically, it outperforms all other machine learning algorithms by a very large margin. In some tasks, it's also outperforming human experts. And something which is very nice with neural networks, which you don't have with most other machine learning algorithms, is transfer learning, which is that when you train for one task, in fact, you find that your neural networks work as well for other tasks that you didn't necessarily plan in advance. So it's very flexible. You can do like basically everything with it, from text translation, playing video games, like learning string theory, properties of Caraballo in string theory. So it's very general. So to go in more details of how it works, so here it's a very simple networks. So we say that we have the input layer, then we have one or more hidden layer, and then we have the output layers. So here, each value of your input is denoted by one blob. So here it's a 3D vector. The hidden layer here is said to have 4 units or neurons. And to go from this one to this one, here you multiply by the weight matrix W1. So here in pictures, it's this multiplication here. Then you apply a function G1 to each of the components of the resulting vector. So again, I say it's really like it's a component element-wise application. So in this way, you get x1, and then you do it again to get the output. So you multiply by a second weight matrix, you apply your nonlinear function, and the result of all this sequence of operation is your neural network. So again, like what you will learn here is this W. And what I didn't display, but you should have in principle, so you can have a translation here by some vector B, which is called the bias. And as I was mentioning in the previous slide, so the goal of learning is really to tune this W so that you can reproduce your function. Okay, so now you have different problems with neural networks. First, it's a black box. So it's very hard to understand the meaning of the neural network's computation. So in the sense that, I mean, you can still try to like see the sequence of operations. So if you give some input, you can see which connection are activated, what are the value of the neurons in the intermediate layer. But in most cases, it doesn't really make sense what's inside. And also, like, it's just making a very long list of computation. So to give you an idea, like state-of-the-art neural networks can have like 500 trillion parameters. So you cannot follow what are doing so many parameters. So we don't know what it's doing. And because of this, you have a lot of problems with like biases. So for example, with underrepresented community, or when you want to do like loan by banks or recognizing photos. So it's a big problem that we don't really know what it's doing, and it can have a like very bad impact on society. Then the other problem is that it's called the loss landscape problem. So is that the loss function which you minimize to try to match your neural networks to the function you want to approximate is non-convex and very rough. So it's very hard to find a global minimum, or at least like a good enough minimum. And in fact, some people try to relate this to the spin glass problem. So it's also something else which is difficult. So training can be complicated. So first, because of the loss landscape, but more generally because you have a lot of computations to do, so it's very expensive. Then you have the problem of convergence because of this landscape. Another problem yet is hyperparameter tuning. So it's very hard to find the best architectures and parameters. So often it's just with a form of arts where you have to know what works, what doesn't work, and just try again, or do some random optimization. So it's also very costly in terms of computational power. So the idea is to try to develop tools to get to improve the analytical understanding of neural networks building and training. So the more you can predict in advance how it works, and the more computation you can avoid, the best it will be for concrete application, and even like going further in developing artificial intelligence.
Harold, can I ask something in this? So when it comes to like learning in this context of neural networks, so you have to feed in a lot of data, right? Also,
yes.
And so is there some estimate of understanding like how much? I mean, whether typically a neural network would really learn more than the input. I mean, compared to, do you see what I want to, like you said in the beginning that it can perform other tasks too. Like if you compare with human beings, humans can have this so-called poverty of input argument that it can learn much more than, especially with respect to semantics. But in the context of this thing, is there understanding, because it's probably not in the list that you mentioned, like how much input it has to take in order for it to learn?
Yeah, so in fact, it's true. Like one other problem I could have mentioned is a problem of data that, like a human, your baby, you show him 3 cats, he knows what is a cat. Like neural networks, you need to show 1 million cats, and then he can still mess up. So it's one of the problems that you need much more data. Then on the other hand, there are some surprising generalizations they could do. So one famous example is GPT, which was used to generate some text. So the idea is that you give some input sentence and the networks should prepare some new text, which would look like what a human could write. So here they found that this neural networks was also getting some understanding of like syntax, being able to reply to questions, making summaries of text. So even if it was not designed to, learn to do this task, it was still able to do them at the end. And what we've found in some programs is that, so even if you train your neural networks on some range of parameters, you hope, it's not you hope, you have seen it in some case, that it will be able to also make prediction beyond the box where you trained. And here's a kind of idea behind this and hope.
Sorry, Harold, are you there?
The screen froze.
Yes. Okay, let's wait for him to come back.
Yeah.
All right. Yeah, so we were discussing this issue of that you were mentioning. There are certain tasks they can perform, although they were not designed for, like semantic syntax recognition.
Yeah, okay. Yes. So here was that. So the second point that we have seen in some cases that you train your networks on some like domain, and then you are able to extrapolate beyond the domain also. So for example, one hope is to use this in lattice QCD, where it's very hard to do Monte Carlo simulation at finite chemical potential. So here the hope would be to do it like imaginary potential and then do some extrapolation to the region of real potential. So okay, here it's the hope. In practice, like we have some cases of in QFT or other where you see that you can indeed do some extrapolation and that it works well. In some other case, it doesn't work at all, but it's definitely learning more than the data you give in the condition that you are careful. So if you're not careful, you will get overfit. So it will just learn by heart the training set, and then it will give you garbage.
Yeah, I had a nice naive question. So when you talk about training, it essentially means this optimization of the nonlinear functions with respect to the parameters. That's something that you keep on changing. Is that right?
Yes, exactly.
Okay, so those are not fixed functions, cannot be fixed functions for a neural network.
No.
Okay.
So you mean which function?
Yeah, that's right. The G's, I guess.
No, so the G are fixed.
G's are fixed.
Yes.
So only W's. So the matrices are. So what is being optimized? I mean.
So So you want to change W. So what you do? So basically your loss function, like the simplest will be you take so the prediction of your neural
I see.
network.
Yeah. I see your so matrix multiplication plus translations and the learnable parameters. So these are the
exactly
one that you keep on changing.
F is really the sequence of multiplication and translation. And in general, you will take the L2 norm of this, so it's the simplest case. So what you want to optimize is this difference between the results for all your samples.
And X size and Y X size are random numbers, is that right?
No, so here it's your measurements, for example. So let's say like if you have like you want to classify pictures. So X will be your image, and Y will be 0 if it's a cat and 1 if it's a dog, for example.
I see.
Or like 0 if it's cat and 1 if it's not cat.
Yeah, yeah.
So in general, it's with what you want to learn, and it's not random because you want to learn some information. So it's with your data. I don't know if you have a Carabio, the X would be like the matrix defining the Carabio, and Y could be the topological information.
Okay. Okay, thank you.
Sir, I had a little question. Am I audible?
Yes.
Yes. So the intuition that we have is that so the neural network is basically trying to say that it's an RG flow, in the sense that if you have an image on the input side and each layer just takes it up to a higher level of change of scales or something of that sort, and then the parameters just keep on scaling up and finally they capture the whole essence. So in a sense, it's like an RG flow following to a fixed point or something. Is that the intuition here, or?
So not yet. So the RG flow I will give is not at all this one. So it's indeed the like intuition that many people had and some papers were proposing. But I think from what I understood, there is no like concrete implementation of this idea. So indeed from images, it looks tantalizing to do this. But if you move away from images for like text or anything, like it's much harder to get this connection. Like as I was saying, like this idea of RG, which focus on features, it's something you can really look for when you have images. But in most cases, what is inside the networks, it's not so clear what it means. And you are kind of losing a bit this scale decomposition. And again, like it was, I don't think there is really any concrete proposal on how to do the RG along the number of layers. So at the end of the talk, I mean, in the second part, I will explain really like how we set up the RG flow. And basically it's a RG flow for the QFT. And so for this, I will need to define my QFT, but it's not counting the number of layers.
Okay, thank you.
And ask me again after I describe the QFT in case it's not clear, but I think it will get clearer when I come really to the neural networks correspondence. And okay, so now the plan. So the neural network QFT correspondence. So the idea is that for very general class of architectures, you can associate a Wilsonian effective action to a neural network. So which means that you can extract a lot of information from this network just by studying your effective action. And this NN-QFT correspondence was pioneered by Iverson, Metty, and Stoner, and I will recommend their paper because it's really a great paper and very clear and a lot of very nice ideas. So in this talk, I want to report several aspects of our paper. So first, I want to describe the neural network's QFT correspondence and add some more details compared to what was discussed there. Then I want to discuss a bit the theory space and what we can expect for the QFT. Then I will establish a RG flow for this QFT and provide some numerical results. And in particular, so the main experimental result we have, in the sense that we checked it numerically, that varying the standard deviation of the weight distribution induces a RG flow in the space of neural networks. So the idea is that before training your weight matrices, you just take some random numbers, so which follow some distribution. So if you take this distribution to be Gaussian, so varying the standard deviation is a RG flow in the space of neural networks. So in fact, it's answering the question, but I will go in more details during the talk. So again, another way to say it is that my RG flow is connecting different networks and not different layers inside the same networks. Okay. So is there any question at this stage?
Yeah, I had another naive question. So how bad can this nonlinear function be? I mean, can you take, for example, a delta function? The one you described is a theta function. Can I take a delta function?
No, I think theta function would be too
bad,
too constant. I mean, so the point that for the gradient propagation, you need something where you would change depending on what inputs you give. Okay. So in something, if you like the motivation that when you have the neurons, like you should modulate the strength of your neurons according to the input. So if you just have like constant even piecewise, I think it would be too simple.
Okay.
So the function with people
because the reason I asked this is the description, the kind of from the description that you nicely described, it does look like one can model a driven quantum mechanical system with this kind of ideas, where the nonlinear functions will act as the drives. So one can ask a question whether I can reach a particular given state or not.
Yeah.
After with a certain given driving, is a state attainable or not in a quantum? So looks like that kind of. So that's why I was asking that in a driven system, one once in a while puts in like shock waves or delta function drives. So maybe a periodic drive also.
So yeah, so this I don't know if someone has tried it. I don't think so. There is a paper by Rod Jefferson and one collaborators on like modeling this more as a statistical differential equations. I mean stochastic differential equations. So try to understand the state of the network. But I have not read in detail. So I'm not sure what they do, but I mean to me it looks a bit related to what you say. So I would read this paper, which I can give the reference at the end.
That would be nice. Yeah, thank you.
But I think the function you get should be quite nice. So first, everything you do should be differentiable. So I think it's one of the conditions on your function.
But your example that you started with was a theta function, which was not differentiable.
Exactly. Yeah. So kind of it should be differentiable up to a very mild singularity in the sense that you can have a discontinuity like this, but not much more, I would say.
I see.
So I'm not sure exactly what like mathematician and ML scientists have found, but yeah, I mean, I know you can allow some singularity, but not too much.
Okay. Yeah, thank you.
Yeah. Okay, so here is the neural networks I will consider in this talk, and we have contained the paper. So here you just have one hidden layer, and you have here an activation function after the to reach the first hidden layer. As you can see, I have added the weight. And then at the end, there is also the second function. In fact, I just took the identity. So here you should imagine first I multiply by my input and translate. I apply my function. Then I multiply again by the weight, translate, and this is the result of my network. So I will call n the width of the hidden layer, so the number of neurons. And the parameters, I will denote them by theta, so which gives you all these parameters together. So my neural network is re-indexed by theta and n. And I take my parameters to follow this distribution. So as you see, there is some standard deviation sigma w for the matrices and sigma b for the bias. And I need to scale them by d and n. So it's basically the dimension of the layer before you apply the matrix in order to get the proper QFT description I will take just after. So the standard deviation I was mentioning as a result is this sigma w. So if you vary sigma w, you get a RG flow. So now we need to have a slight change of perspective compared to like more applied machine learning. So in machine learning, you just take one networks which you initialize according to this Gaussian distribution. Then you do your training and you get one networks and you use it to make predictions. Okay, here it's not exactly what we do when we look at this NN-QFT and so on. So in fact, we consider a statistical ensemble of neural networks defined by the distribution in parameter space. So we don't want to look at just one network, but we just want to look at, in average, what is the behavior of the networks we get given the architectures and these distributions. So in a specific neural network, it's just one sample for this distribution. And the idea here is to really understand the distribution by itself, just not like a single instance. Now, because of this, you have a dual description. So if you take the distribution in parameter space plus the architecture, in fact, it's inducing a distribution in function space. So instead of seeing the networks as defined by this distribution, you can see the networks as a distribution in some function space. And training So it's a change in the parameter distribution. So you don't want to move from this randomly Gaussian distributed variables to some new distribution, which kind of give you a neural network which makes the prediction you want. And the idea here is that training should be quite insensible to the specific initialization and process, such that at the end, if you train again and again, you are always getting neural networks performing basically the same task up to some minor variations. And so this training, you can also see it as a flow in function space, so where you move from some general like random function set of function to a space where you just get a subset where you just get function which are really making the approximation of the function you want. And just to mention that in this NN-QFT correspondence, so I will not discuss training today, but in this paper from Halverson, Metty, and Stoner, they are discussing a bit of training. So it's also a very nice paper.
Sorry, I didn't get this notion of a function space. So it's a function is a function of the parameters, or is it a? So what exactly?
So you have two ways. So first, if you look at as f indexed by the parameters, it just, I mean, you take your parameters from this distribution and you build your function according to this way. Another way to work on it is just to say that f itself as a function, so it is a sample from some distribution in a functional space.
Okay, it's
So by
a
forgetting who is this
functional
parameter. Yeah.
Okay.
And I think it will become clear just on the next slide,
Okay.
because we move to QFT and here, I mean, it will be clear what I mean by this. So in the large N limit, so it corresponds to when you take the infinite layer width. So the intermediate in the hidden layer becomes infinite. And what you can show in this case that the neural networks as a function distribution, so is drawn from a Gaussian process with some kernel K. So here it's what now we mean by you can also see as the function, so a distribution in the function space is that you get a Gaussian process in the space of function with some kernel K. And so your neural networks now will just be one sample of this distribution of this Gaussian process. And you can see this as a consequence of the central limit theorem. And the interesting point that this generalizes to most architectures and also with training. So is that even if you take like a very general networks like people are using for practical purpose, this is still true. So it's quite nice because so what we are describing here is not like a very specific setup where you need to fine tune a lot of things and which have no chance to apply in real life. It's really something which can apply to what people are doing in the industry and so on. So now the idea is that given this Gaussian process, you can write the log likelihood, which so is a functional called S0 of f. And you can compute endpoint correction function given this log likelihood. So here it's really what I mean by the fact that f is taken from a distribution in function space. So that you can write a path integral over f with some weight S0, and you can use it to compute a correction function. So psi is the inverse of the kernel of the Gaussian process. So as you see, like I'm not making any more reference to the parameters. So now I'm just working directly with some distribution in function space given by this exponential of minus S0. So does it answer your question for this you had, Ian?
Okay, that you may have answered, I may not have understood. So this f is the function that takes an input and maps to an output, right? For a given network.
It's a neural network, yes.
I see. And how do you get the kernel? The kernel is simply how do you?
So it's not trivial. So you have to compute it given this. So you start with this function here, so where it depends of W, G, and so on. Then you have to make some computation to get K. But I mean, you can do it, and they make the computation explicitly in the paper of Halverson and collaborators.
And that depends probably also on the architecture and other things.
Yeah, so by architecture, I saw the G and the, so this depends on G. So if you change G, then you get a different K.
Okay.
So
okay,
so
thank
so
you.
like K and psi we depends on G and all the W and B in principle.
Okay, now I understand.
Not W and B, but the sigma W and sigma B and N.
Yeah, the distribution of the.
Yeah, exactly. So it depends on the distribution and the architecture in the sense which nonlinear
G1 is
function you
still
have. Yes, exactly.
Okay.
So now like we can say that, okay, if you took cycloduck, swim-raxoduck, and quark-cycloduck, okay, it's a duck. So, okay, it's not a good citation here, but as you can see, it really looks like a free QFT. So for us, it's just like a free QFT with some bilocal kinetic term. So what we do from this? So now for finite n, we get a non-Gaussian process, which means that we get deviation of the green function with respect to the pure Gaussian case. So in QFT, we will just say that non-Gaussian contribution or interactions. So what we do is that we build an action, F, which is some free action plus some interactions. And now the point I want to stress here is that the free action S0 prime is not known. So because the point that it's the full action here, which in the largest limit will become the S0 I have written in this slide. But this free term is not just S0. It's some, I mean, it's way more complicated. Like the limit, you depend also on the interactions, which makes sense because you know that here it's like the microscopic kinetic term. And you know that the propagator, and so the we get quantum corrections from the interactions. So like the kernel of the Gaussian process is what you get after taking into account all quantum corrections. So in some way, so another way to say is that this S0 here in the largest limit should give you the propagator and kinetic term of the 1pi effective action, not of the like microscopic theory in presence of interactions.
Yeah, sorry, I have a confusion here. So in the previous slide, when you write the zeta, capital zeta, the K inverse, the zeta should be 1 over x prime square if it has to be something like a non-interactive theory, because it has to be related to something like two derivatives with respect to x prime.
Not necessarily. Here it can be very general. So here it's one of the points that it's not, we're not doing like, you know, condensed matter or high energy physics. So in principle, it can be any function you want of x and x prime.
Yeah, I was, so my question was that for a free theory, I would have expected it to go like that.
Yes.
Second derivative theory, right?
So here's the point that when I say free, it means just that I have a quadratic term. But in fact, you could have like infinite number of derivatives. So in particular, when you will get a biological kernel,
my question was, is the fact that standard free theory is related to this quadratic related to the fact that you are talking about a Gaussian process?
Yes. So it's quadratic because it's a Gaussian process.
Okay.
But you know, like, I mean, it's free in the sense that if you just have quadratic terms and you write Feynman diagrams, you will never get, I mean, you will not get quantum correction or anything.
That's right.
Split.
So the fact that you are taking a Gaussian process led to the fact that this xi is 1 over, I mean, 1 over quadratic.
Yes, exactly.
As a distribution. Yeah. Okay. Thank you.
Exactly.
Yeah. Okay.
And so now here we move away from the Gaussian process.
Yeah, that's right.
And then so it's like adding interaction. So you need now like it will become more complicated. So you get green function.
Harold, just a short question. So you are saying that this S of f that you're computing now for finite n, that is like a 1 pi. So there is no concept of loops actually. Then
no. Here it's a microscopic theory. So here from this action you have loops.
Okay, from this action you have loops.
Yes. But so the point that what you should recover, so is that the 1 pi action, so like if you compute the 1 pi action from the path integral, so the kinetic term should match this.
Oh, this is the exact 2-point function.
Yeah, so here it's the exact 2-point function, so it's with a 1 pi. So in the large n limit, it's just this for everything, because you don't have loops or anything. But
so basically, it incorporates, your n is more like an h bar, and 1 over n is like an h bar, and your exact 2-point propagator has all these loops. all 1 over n corrections incorporated.
Yes.
And then that gives you this S naught F that you showed in the earlier slide. But S naught prime F is simply the microscopic
Exactly.
thing that,
Yes.
okay.
Exactly.
So, but is there a way to, so the question that they want, is there a systematic way to derive this microscopic S of F? Maybe we are going to talk about it.
This one, no. But I will talk about it. Like there is no way to get it. But because renormalization, you don't really care about like specific microscopic details. You just want to be in the good universality class. So the trick we use is that we just take an action which allows us to make the computation. What we want to make sure is that in the infrared, so the effective action is that we recover what we want.
No, I'm just saying, just from a point of view, it might be indeed interesting, like Kaushik was asking, to understand what is this S naught prime F. So that is analog of the free, the true free theory in some sense, right?
Yeah. And so you cannot get from the data you get from the neural network construction. So, but if you follow, like if you compute this K, like by the method described by Iverson et al., you cannot just, I mean, you then have no way to remove to S0 prime. You know, it's like in QFT. If I give you the infrared, it's very hard to go back to the microscopic theory. Like if you just, I mean, if you are at the infrared fixed point, you have lost so much information, you cannot go back to the UV.
I see.
In a unique way. So here it's really the same problem, is that I give you the infrared. The question is, give me some UV which reproduces, and you have too much possibilities.
But one would at least like to see if there is some 1 over n deviation. Like for example, in some sense, one could actually, if your S naught F is n goes to infinity limit, then something like a 1 over n corrections should be possible or impossible. In this.
So in fact, it's kind of what it's written. So here where I was coming, that so.
Okay.
So here, okay, it's another way to say it is that so the effective or infrared 2-point function is exactly known. So this G2 of X in this theory is a kernel K, and it's equal to the G02, which by 0 I will mean the Gaussian process theory. So not, I mean, 0 is not the free theory here with prime. And one way to see it is that in fact the kinetic term, I mean, so this 2-point function is n independent. And what you can show by studying by how you build the QFT from the neural networks is that the connected green functions scale in this way with n. So in the same, so because of this, when you rewrite the interaction, you will get a power of n. So I think it's related to your comment about like n is kind of playing the role of h bar.
Yeah,
so, you know,
exactly.
Like,
yes.
So it's because of this that at the end, so I mean, you can really show that this should be independent of n, and it's why, so like your exact 2-point function should be the one you already had for the Gaussian process. But now, if you go back and you just write some action here, you know that what you get here is not this 2-point function. So you need some more work.
Here, Harold, I have another confusion here. So this is since you start from the kernel in the S0 prime F. This is always going to generate derivative interactions. Is that right? So momentum dependent. So or not?
Yes. Yeah. You can have derivative interaction, but not that. So the kernel is not in S0 prime. It's in S0. So this we don't know what it is.
I see. Yeah, but okay, I see. So you're basically trying to find out some kind of interaction which will mimic the it in some sense iterations in the neural network. Is that?
Yeah.
Okay.
So what you really want, in fact, is to find the one PI action.
Yeah.
So which reproduce what you compute with the neural networks. But us as physicists, we prefer to work in general with a microscopic theory. So what we do, because you know, like the one PI action can be very wide and so on. So what we do is that we work in so when you compute Feynman diagrams to match like the results of the neural networks with the QFT, we are kind of working with the exact propagator.
Yeah.
But the interactions are made of the like microscopic interactions. So you know, you do something in between, like you have already resummed the propagators, but the interaction, you don't do it. So for example, if you have a loop, so the loop uses the exact propagator, but the interaction are still the one of the microscopic theory.
I see. So it's a kind of semi-classical.
Yeah, I mean,
well, I mean, it's semantics, but yeah.
Yeah, I mean, in principle, you can include as many loops as you want, but what's nice is that because you have this 1/n, so you can decide when you truncate with n. So yeah, you can throw away some loop thanks to this. But the propagator itself is full quantum, for example.
Yeah.
So here is a small summary of the correspondence. So here we see that space-time points are mapped to data space input. Momental space, it's a dual data space. So the field is a null network. The propagator is a Gaussian kernel of the Gaussian process. The free action is a log likelihood, and interaction is non-Gaussian process corrections. Okay, so we have this map. So in general, we just use any term interchangeably, and I will prefer to use the QFT language. So now let me discuss a bit the data space. Just before, so Ian, how much time do I have to know?
15 minutes at least, but we can go over time also, no problem, depending on questions. So don't worry too much.
Okay. So if at some point I need to speed up, just let me know, because I still have a lot of slides to do. So just, I mean, I'm fine with going on as long as people want, but if you get bored, just tell me. And
no, you can speed up a little bit maybe, but don't worry about time.
Okay, great. So so the main point is that data space is not space-time. So we should avoid the bias we have from particle physics or Connor's matter. Even Connor's matter is a bit more general than what we do in particle physics, so it's good, but we should really stay really open-minded. And just to say, so in the original paper of Halverson and collaborators, they were really working with a particle physics point of view, and they made a certain number of assumptions which to us seems like completely valid in a particle physics context. But neural networks are just really a different type of object, and it's hard to see how much you can expect from particle physics to just propagate in that case. So here in spacetime, so spacetime is really a set of points to which you also give a group structure and some causality conditions. So in Pana, you can so these how coordinates can be transformed, so that you get invariance by translation, rotation, or permutation of coordinates. And you also have some locality principle, so from the kinetic operator, but more generally, you want to prevent causality violation. So now when you start to have these conditions, it's kind of restricting a lot the kind of action you can write, as we know. But in data space, what's the meaning of the group structure? Clearly, we don't necessarily have to work with Poincaré. We don't necessarily care about causality, because what it means to have causality in your data space of images, for example, and so on. So it means in general we can have a bilocal kernel, and then maybe not, why not no co-interactions? The question is, what are the symmetries of the inputs and outputs? And the point then is that we have also a natural UV cutoff, which is a machine precision. But the main point is that everything we expect from particle physics, it's not clear that we should still use it now. So what we do is what we could call neural networks phenomenology. So we make assumption dictated by numerical evidence. So you start to write some code, you see what you get, you write an action, and you try to reproduce the results you have. So if it works with something very simple, it's great. So some local particle physics-like model, perfect. If it doesn't work, then you can just start to react the assumption you have. So it's good to be sure of which assumptions you're making. And then you can also use a model to check some theoretical facts like dualities and so on. And for these kind of things, I will encourage you to read the second paper by Halverson and collaborators, where they will try to do these phenomenological aspects of studying symmetries, like checking other facts and so on. So what kind of assumption we make? So in general, in this talk, so we will look at local interactions, which is what you expect from particle physics. So you just get a polynomial in F with different coupling constants. But in fact, if your kernel is non-local, you can just as well get non-local interaction and coupling functions. So you get something general in this way. And in fact, so like Iverson and collaborators didn't want to have non-locality because our coupling function, because I was mentioning that you can generate translation invariance. But in fact, if you will have a very general non-local function and non-local coupling function, you can still get translation invariance here. So invariance is still possible. Another aspect is to use delocalized fields. One interesting aspect is that they have a good UV behavior, like in string theory, for example. And finally, the more general things you can do is to use tensor models, which amounts to break the permutation invariance. So in a tensor models, instead of writing f of x, where f of x mu, where each f is depending on each component of the same x, in a tensor model, like every f is just depending on any component. I mean, can depend on any components of the coordinates you use to write the action. So if I have a cubic monomial with 3 x, y, z, I can decide to distribute my x, y, and z of each, the components of each of x, y, z in any of the function. Now the point of tensor model is that you cannot permute components. So like in for a normal scalar field f of x, I can just permute x1 and x2. So it's just a question of a label. So
sorry, Harold, I'm losing here something. So you started with some f of x, and how suddenly it become f of 3 variables? So it's
just in a way to write it more explicitly. So like when I write x, in fact x it's a d-dimensional vector. So when I write f of x, I really mean f of x1, x2, xd.
Yes.
So here it's really like it depends on all of the components. The point is that in general, when you want to have something which is Gorans covariant, you will just need to write a f which depends really on x mu. You cannot write x1, x2 separately, otherwise you break Gorans covariance.
Yeah, but then why don't you simply write e to the power tx times fx cube? Why you write it this way?
Sorry, here, this one?
Yes. No. In the equation, yes.
So I didn't. So can you say again?
If we simply integrate over all x and write as fx cube, so why it is different from the way you are writing it now?
So here it's because you see that in this f, I have the first component of x. Oh, okay. What you mean is that here I could call this x, and this I could call it y, and it would be just a change of variables, right?
Yes.
So the point that if you do, so if you were doing this, then you would just get like the integral of f to the cube.
So, yes. So I have a more fundamental question actually. So your d cube x is essentially right. If I understand, it would be f of x1, x2, x3, right? Right. That is. So here you're somehow changing the arguments of the function in a very funny way, right? And this is not how we usually do, or even this. I mean, I haven't seen a field theory definition ever. Maybe it's just I don't know at all about this kind of field theories. I've never seen anything like this in field theory at all.
Yes. So here one way to understand. So the idea is to say that when you have so the one component can always only go in the first slot of this function. So another way to say it is that you have no permutation invariance. So you have no ON or even just permuting entries for this function. So so when you have a scalar function anything, I mean x, you can always do a ON rotation. So if you want to break this, you need to do something like this, which is a bit funny. So where you say that, okay, you could have x1, y1, z1, but then it just, I mean, you don't get any interaction because the different fields don't speak to each other.
So basically, you're saying that
I think this he doesn't in this particular case he doesn't care about the Lorentz invariance or something, or rotation invariance or anything. So think of this first f as a function of both x1 to x1, x2, x3. such that, I mean, in general, but the derivatives with respect to x2 and x3 are 0. So,
yeah, so
I think
another
the
way
kind
to
of question you are asking is related to a Lorentz invariant or rotation invariant field theory. Here, this is not
No.
even rotation invariant.
no, I understand that, but I think what you can do is that instead of having like 3 independent rotations of x, y, and z, you can have only one global rotation symmetry.
But then that probably will bring in a permutation invariance. That will be a subgroup of that.
Yeah, it will be some kind of
Right. So he is breaking permutation invariance, so he has to break the bigger group anyway.
Yeah. Okay, I see. And
So-
and what about this delocalized field? I'm embarrassed also. I have no idea about it. I've never.
So
this is like the shadow operator, if you remember. Think of the kappa as the 1 over x minus y.
Okay.
This is exactly like a shadow operator with a particular, I mean, a general. In the one you put in CFTs, you put in the shadow operator, right?
Yes, this I don't know the shadow operator, but
in that case, this kappa xy is just 1 over x minus y to the power 2 minus something, the conformal dimension. So that kind of a thing. So yeah. And if it's 2, it's a second derivative. You can actually implement derivatives using residues for the for these guys. Yeah.
So here, for another example of delocalized field, for example, if you take the kernel to be a Gaussian, so for example, exponential of minus x minus y squared.
Yeah, if it's a non-Schwarzian type of distribution, you will have it delocalized.
Yeah, exactly. Yeah. So it just some way to say that you don't want to have local interaction, but that the non-locality comes from just smearing each field to like a small region of space-time.
Okay, thanks. Okay.
And so to come back to here quickly, so just to help you maybe to see better, so just to mention that this type of action here is really too wide, and you know, like I could decide to set like x equal y or this kind of thing, but this is too wide. So if you just write this and you break all symmetries and so on. So if you restrict to random tensor models, so where you see so all this as we're indices, where you can have only pairwise contractions. So for example, here I will need to set like y equals z, and then I will get some like contraction between the different f seen as tensors. Then you can also have some kind of, so you will need to introduce some invariance, and then things get manageable. And one example of this, which maybe could help to clarify, is matrix models. So if you take just the a 2-dimensional, so 2 instead of 3, so I take 3 fields, but let's say I remove the third component. And I take y equal, so, okay, I would have to see, but I think if you take y, no, not y equals z, but so imagine here you have a cubic matrix interaction. So you would have this x1 contracted with this field here. So this z2 contracted with this, and then sorry, let me check. No, it's not exactly this. So okay, okay, sorry, it's a bad example. But in matrix, you can do something. Sorry, this was confusing. So a way to see it when you do matrix model is that each of the index here will be associated to a strand. So if you have a matrix model, you will get 2 strands, and you know you can get this type of diagrams here. So now when you have tensor, you will just get 3 strands. So you will get 3 things like this, 3 coming here, and then you can see how you attach them to each other.
Yeah, okay, I think I get a feel of what you're saying. Okay, thanks.
Yeah, I'm sorry, I will need to draw much more diagrams to go into the details. So there is this books, which is quite nice. And so in the paper, I don't think we give a lot of details because it was just a side comment saying that in principle, you can use as tensor models. But
yeah, it is simply a very high infinite dimensional tensorial contraction. Yes. That's all, right?
Exactly, yeah. So you can reimagine this as like, you know, the like ribbon diagrams of matrices, but instead of 2 strands per line, you get D. So here you would get 3. And then when you connect them from the different legs, you just look at all the possibilities you can make. And this is a tensor models and what you get by this action when you restrict to tensor models. Okay, so now let me set up what we do in this talk. So in the talk here, we take d out equal 1, and I will look at a translation invariant activation function. So G is of this form. So you see that I just take the exponential of the result, so the result of multiplying the weight with the input. And then I will also introduce some normalization. So it's not, strictly speaking, just activation function, but it's activation plus normalization. And here you can compute the Gaussian process kernel to be this. So you get a constant term plus a k of w, which is given by this. So as you see, like it's a Gaussian. Okay, now you can try to do the numerical work. So first, for numerical, I also take d in equal 1, sigma b equal 1, and I will look at n with all the different values. So the idea is that we take n bags of distinct statistical ensemble of n net networks each. So what does it mean? So it means that the experimental or numerical green function are computed in this way. So first, you compute the correlation function of your network in each of the statistical ensembles. So here for the correlation function, as you know, so it's really like, imagine you want to study correlation for a function. So you just take the product of your function, and then you average over all the possible nets. Now, what we want to do to get some idea of the statistical deviation is that we do this n bags time and repeat, and the green function I will quote, or the average over all these n bags. So then what you can do is that you can measure the deviation of this experimental function compared to the exact, so the Gaussian process green function. And we can compute also the normalized deviation. So then to do this, so we take 6 points, which are like these different values, and we evaluate the green function for all the unique event combinations. So for example, the G2, I think you have like 21 different combinations of all these points. For G6, you have something like 500. So you compute this for all combinations. And then you want to try to use, to write a QFT to reproduce this green function you get numerically. So the local action we write is the following. So S0 prime is not known, so prime is missing here. And then we consider quartic and six-tick interactions. So the numerical results we find.
Harold, if you don't include symmetries, even at the level of U4, there are like enormous number of possible terms, right?
Yeah, exactly. So here it's kind of the point of like doing phenomenology, that so we write the simplest model we can, and we try to match with what we get numerically. If it works, then we stay with this action we found. If it doesn't work, then we need to include more interaction to try to describe better what we observe.
So basically, you do something like the MSSM people do, like do some select your parameter space, but then you could in this way experimentally confirm some emergence of some symmetries, right? Because yeah, okay, I see.
Exactly. Yeah, at this stage we have no understanding of what are the symmetries of this neural networks QFT. So it's not like even the standard model or MSSM where you can still constrain the general form and then try to make more assumption. Here, in principle, everything can go. So okay. Because it's so vast, like you just want to start with the simplest and see if it works. And if it doesn't, then remember that you just did something very simple, so that you need to do more complicated.
Okay, thank you.
And so from the numerical result, we find that M2 is 0 for all n, which is good. So n than the 2 and 4 point function of 1 over n, which makes sense because here we are not looking at the connected green function, so we expect that there will be 1 over n in general. So to extract a single number, we will average the absolute value of the deviation over all combination of point x1 to xn. And we also compare to a background. So for the background, we take the standard deviation of the experimental green function over all bags, and then we average over the points. So here are some graphs. So as you can see, so we have plotted the values of M2 for all the different points we evaluated here. And they are all very small and centered around 0. So it tells you that M2 is basically 0 as you expect, because we know that the exact 2-point function which we get from the numerical result should match the 2-point function of the Gaussian process kernel. Now, if you get M4, as you can see, like when you start at small n, the value, so the deviation are very big, and as you increase n, it's moving towards 0. And the same for M6. So here you are already seeing that indeed you have like 1/n effects. A better way to check them is to look at this number, so the average of the deviation over all possible points. And as you see, so M2 is always clearly under the background. And for M4 and M6, it's not as clear, but you see that as you move toward large n, you start to, you get below the background. So you need to go to, to go to very much higher n to have a very clear signals, but it was too computationally expensive. But the point that here you really see the 1/n trend of this deviation.
I'm
Okay,
sorry,
now,
I need to ask something again. So, okay, maybe you're coming to it. So if your X is very large, then you have an enormous number of, say, 4-point vertices, right? And even if you assume something of like tensor network type or this tensor field type, so then, so doing something like this is extremely expensive, right? I mean, you do averaging over such.
So here it's not expensive. In the sense that I'm not using the QFT yet. So here it just results from the neural network. So now I'm showing with this computation. So the F
right
here is defined by as a neural network. So I'm just doing. So I'm defining neural. So I'm taking like so you see like the number here. It's like 20 times 30,000 neural networks. Each is taken from this Gaussian distribution of the weight parameter, and then all of this F here, I'm just computing the sequence of matrix multiplication and so on.
Okay, I understand. Now, here, of course, it's not expensive, but eventually, when you compare with the
so this will
then
come
it should
here.
be real. Okay.
So now, like I want to evaluate my U4. So U4, I can see it as the exact green function minus the disconnected part. So the numerical computation I gave before is giving this. So now I need to subtract these graphs and I can have an evaluation of U4. So here in my action, I assume that U6 is small, but from what you said, so if you have more like contribution to the quartic diagrams, then in the left-hand side, I will not have just this quartic simple interaction, but I will have much more with some complicating form factor and so on. So the difficulty when you have more interaction doesn't really come in the problem of computation first, but we're already trying to find how you extract each of the coupling constant or function.
Okay, so here you're just simply, after all, going back to particle physics and
exactly,
and
yeah. You just use Feynman diagrams, and here I just assuming that U6 is not contributing, which is particularly fine in the large n limit because we know that U6 is very small in that case. So to get U4, in fact, it's just the deviation of the experimental green function divided by this factor, which is just you're truncating the external legs, like we do in particle physics. So you can evaluate this numerically. And the result is that we found that, in fact, U4 is approximately constant and negative. So in parallel, because it's negative, it means that you really need to have a U6 bigger than 0 or any higher power for the path integral stability. And in fact, in this original work from Iverson et al., they studied only U4, but in the absolute value. So they concluded that U4 is sufficient to describe your neural networks, but it's not the case because of this stability problem.
But again, I mean, here, essentially, you're motivated by studying an EFT without symmetries. but again, it's like this ultra local assumption is still a very strong assumption. And
yes, exactly.
So what is the evidence that it indeed is the correct
so the evidence is that if you compute this ratio here, you find a constant. If you were obtaining something which would not be constant, then it would tell you that, I mean, here you will get 4 tensors. And so that the form of the regional action is not good because you started by assuming U4 equal constant.
So, okay, I understand that. So constant, you mean is independent of this x1, x2, x3, x4?
Yes, yeah. And
but it's constant at the right order and the same order in right? This is constant in leading order.
I mean, it's also constant for n equal 2. So.
Okay.
And so I just realized that I forgot to insert the graph. So, okay, so I will show you the, it's something, I forgot the graphs. But so basically what you see is that U4 is just, so like so if you plot in log space, it's quite big when n is small, and then it just goes to 0, like as 1 over n, as we expect. And now if you plot it like with a sign, it's starting, you get a curve like this, where it's going to 0, but from the below the axis, so it's negative.
But for me, it is very surprising that even for n is equal to 2, that it is constant at all.
Yes.
So I have an understanding why.
So my hypothesis is that it's because we have a translation invariant kernel, which is kind of making, I mean, favorizing to have local interactions. In fact, so in this paper, they studied some, I mean, what happens if you take into account non-local corrections. Not very general, but some like very simple corrections. And they found that it was not really improving the result.
So in a way, what it is saying that what you're trying to say, if I want to paraphrase, is that this EFT treatment enables you to see these hidden symmetries, which you couldn't have seen otherwise, but it doesn't explain where they come from yet, at least.
Yeah, exactly.
Because here you are simply, but if you would have to see this, you have to somehow take all possible couplings and show that this translation invariance indeed acts like some kind of fixed point or something.
Yes,
but then
it's one of the big problems. So in fact, in this paper, so they add several terms together at the quartic term order, and then they just like do again all this computation, and they ask, okay, what are the best value of my parameters to reproduce what I know, and then they find that it's basically the constant things which dominate.
But you cannot it happens only with just 2 layers. Even if you have 2 layers, it's enough to produce translation invariance. That's really surprising.
So translation invariance, in fact, is produced by the kernel. So it's not the number of layers. And in fact, if you look at, so they looked at 2 other kernels here. So the activation function. So one is the ReLU, so the one I said at the beginning like this. And one is given by the R function. So in these 2 cases, the kernel is not bilocal and not translation invariant. But surprisingly, they found that a constant U4 is still fine to describe the numerical results. So which I find even more surprising.
Yeah, but this experimental thing that you're generating is not translation invariant, right? It's experimental.
So it doesn't look so first because you have all this x1 and some dependence.
Exactly.
But if you evaluate numerically, you find that it's just constant.
Yeah, that's exactly what I'm saying. That
yes.
So isn't it? So from a numerical computation, okay, we don't know how to get the kernel for n is equal to 2 explicitly, right? That's what we said earlier. So what I'm trying to say that the fact that it is coming at n is equal to 2 already is extremely surprising.
I mean, so we know how. So the kernel we know to get it at ON. So because we work as we use the exact propagator. So here it's the exact propagator.
No, what I mean is as follows. I understand. I understand what you're saying, but I'm just saying that this S0 F you do not know, or at finite M, so you do not know that you have no idea about the microscopic description, like microscopic EFT.
Yes, exactly. Yes.
Yeah, but then the very fact that even for n is equal to 2, you get this translation invariance is rather surprising to me.
Yes, exactly.
It's,
Yeah.
very,
and especially when you start with a kernel which is non-translation invariant.
Exactly. So what I'm trying to say that this EFT is a way to probably discover this kind of new
yes,
symmetries
yeah. Okay,
coming
sorry,
out.
Yes, exactly. Yes.
It's a way to discover these new symmetries, but or to establish that these symmetries are there, but it's still but it doesn't tell you why they're there, right? Yet.
Yeah, exactly. Yes. And it doesn't tell you if it would be here if you have like 2 or more layers or more complicated like convolution networks and so on. So the question is that, is it the case because it's a simple network, or even, you know, like in principle, okay, I don't think it's the case, but we look at these points here. Like if we look at more different points, would we get something like if we go to very large X, for example? So I don't think it would change, but in principle, it's possible that it's, you know, like by mistake, we just went to a very specific region or something.
Okay. Yeah. Okay.
I don't think it's the case, but in principle, you know, like we make a lot of assumptions and create like many places. I mean, like we get explanation of why it works like this.
Thanks.
Which is why it's also useful to have both with the numerical and the analytical side, because then you can try to understand better. And indeed, the goal is to try to get as much understanding as we can on this QFT. Okay, so I will move to the next section, and in view of time, so I will try to get quiet fast on this. So here, how you do the non-perturbative RG flow. So first, when you start with a partition function and microscopic action, you can define the partition function with the source and the generation function of connected graphs in this way. And so S here we encode the UV or microscopic physics. Now you can define the classical fields by varying with respect to the W. And the 1PI effective action is defined as the Gaussian transform of W. Okay, so this we know well, and gamma encodes the effective or infrared physics. Now, so the renormalization group flow, the idea is that you want to organize the theory according to length scale. So you want to integrate the degrees of freedom step by step. So you don't want to integrate over all the phi in one go, but to do it step by step so that you get something which interpolates between this S and this gamma. So the very simple way to do it is Wilson and as we learn like in particle physics. So you just split your fields in fast and slow and fast modes according to just a very like hard theta function. So then you can decompose the kinetic operator in the same way. And the Wilsonian effective action is just you get the kinetic term for the slow modes, and then you get an effective interactions, which you get by integrating over the fast modes in this way. Okay, so this is not very convenient to use a hard cutoff. So in general, we will use a smooth regulator. So you define a xk of p, which is your previous kinetic term multiplied by some regulator. And you want your regulator to go to 0 when p is much bigger than k, which is like the scale where you want to separate fast and slow. And it's 1 otherwise when it's very small. So now, because you can split your kinetic operator, this also like inducing a field decomposition in slow and fast modes. So here, not now that sky, so which is the slow mode, is not anymore like just the restriction of phi for p less than k, and this is not the restriction of phi for p greater than k. So you get some like intermediate range around k where you need the modes of the two fields. But at least what you can say is that the like free measure is splitting in this way. I mean, just factorize. So now you can do the same thing as before. So you can compute the effective action at scale k. And let me note that this k is a UV cutoff for the slow modes chi. So we do the same. So we get some effective interactions. And you can show that this effective interaction satisfies the Pochinski equation. So, okay, I mean, I don't want to go into the details, but you can just in this way, we imagine a flow in series space as you move K. So the problem of this equation is that it's not very convenient to do a non-perturbative truncation of the Pochinski equations. So Wetterich proposed another formalism. So here you regularize the path integral by introducing some regulator here, like a mass term, which can depend on the momentum and also this parameter K. So note that now my kinetic term in S is still the original one. So sorry, just psi. So you want a cutoff function so that when K goes to infinity, you recover the microscopic action, and when K goes to 0, you recover the generation. Generation function here. So for this, you need to have a cutoff with S properties. And now we can define the classical fields again in the same way as before, and we define the effective average action at scale K as the Lagrange transform. But now we need to have some correction in the Lagrange transform to be sure that we satisfy this condition. So here you see that for K equals 0, we recover the effective action, so the 1 pair effective action, and for K infinity, we get the microscopic action. So here what's funny is that in this formalism, so K is an infrared cutoff for the classical field phi. Now you can derive the Wetterich equations, so which tells you how this gamma K is changing when you change K. And for solving this, you need some approximation. So you need to restrict the series space to a finite dimensional subspace. And you have people who use a derivative or local potential expansion. So what's nice in this formalism is that it's non-perturbative, so you can just work with finite coupling constants. And we will also use a large n expansion, so we keep term. So keeping term up to 2n means that you are going up to 1 over n to the small n minus 1 effects. Okay, so now machine learning. So why we can do this renormalization group? So I was mentioned in the introduction. So in machine learning, people tried to use some RG flow in machine learning, which looks natural because you want to find a pattern in a large data set and ignores the noise. And you want also to try to find some idea of this decomposition in scale of your neural network. So here we don't exactly do this directly with a neural network because, as I was mentioning, it has not been very clear how to implement. But you can do RG flow for the QFT you get in this correspondence. The only thing which is a bit tricky is that here we know the effective action. So we know like the effective propagator, which is from the Gaussian process. And we also know the effective interactions from how you measure numerically. But we don't know the microscopic. So it's really the opposite as yours. So we need to kind of reverse the flow. But information is lost and we don't have a one-to-one map in UV-IR. But that's fine. So we can take any microscopic theory which is the same infrared universality class. So it's kind of this. So here we know the gamma. And we can start with any action which under the RG flow we move to this gamma. And I just want to quickly mention that in these papers I also defined the RG flow, but they did it with respect to what we would call the infrared cutoff, which is also a bit funny, but they could get good result because at the end it's just a consequence of scaling, which you can prove within the framework I will describe. So is it clear for this picture here?
So just stupid question. What is this RG flow parameter here?
So I will come to this just next.
Okay.
So in fact, we have two possible parameters. So before introducing this parameter, so let's look. So the momentum space propagator. So if you take the kernel I had given and you go to momentum space, you get this. So here you see that you have an exponential minus p square. So it's like very soft UV behavior. And you can also do a momentum expansion when p is small. And you see that in fact you can approximate this k in this way, which is looking like a standard Klein-Gordon propagators with some mass depending on the sigma parameter.
No, what I actually wanted to ask is, Harold, is in terms of the original data, suppose I did a numerical experiment and then I want to match at some RG scale. What is this flow parameter?
Yeah, this I will come to it. I mean, I need one more slide, I think. But
I will probably something that you already said before that you're
okay.
Kind of
okay. So the
dual space.
So I have two parameters. So the first one is the sigma W. So this you can use this as a RG scale.
Okay, so essentially that is sort of a cutoff in your momentum space in the if you look at the actual data and go to dual.
So it's a cutoff because here you have p square over sigma. So when you tune sigma, you are kind of timing the UV. So you can see this as a UV cutoff. The other things which you can use as a UV cutoff is kind of the machine precision. So where you kind of restrict your integral over like some precision, which you interpret as being what your machine can represent.
Okay, thanks. I understand now. Okay.
Okay, in fact, yeah, so in fact, it was just here. So yeah, so we have the machine precision or M0 as RG scales. And for the effective action, we do this approximation. So we will take some kinetic term, which I will describe later, and then we will just make the assumption that it's local. So by phi4, I will mean integral of, dx phi4x. And here my coupling constant depend on k. So now we have two different points of view for the RG flow. So we have what we call the passive RG. So we keep the mass M0, so the correction length fixed, but we vary the machine precision. So it's like fixing the neural networks and varying the data. So it's kind of this picture. So you start where you have some grid where with a machine precision much lower than your correction length. And then you derive this grid, and this is inducing your RG flow. The second case, you get the active RG. So here you keep the machine precision, but you vary this effective mass. And here it's like deriving this correlation length. Okay, so for the passive RG, I will be very quick. I mean, we derive the flow equations. And just here, let me mention that we could not really find a way to make a numerical test of this because we are not sure how to relate the K to the machine precision like as a numerical parameter and know exactly what we need to compute numerically to check these equations. So in particular, if you have an idea at some point of what we need to compute to test this equation, it's great. Now in the propagator case, so here, as we mentioned, the propagator looks like a zero momentum propagator with the UV regulator with scale K. So the idea that changing the standard deviation is like changing the UV cutoff, which defines the running scale. And the point that if you have a classical action with this propagator, it's satisfying the Pochinski equation. But here we have a problem because we don't want the classical action to satisfy the Pochinski equation, but the full effective action. So a way to deal with it is that we need to impose some condition between the kinetic term of the action and the regulator we choose, so that what we get at the end is always the kinetic term of the 1pi action. So we get some flow equations, and written in terms of sigma W, you just get this. So it's like pure scaling. So here let me note it's quite nice because you go from just some parameter K, which look a bit abstract, to something which is really related to your neural networks. And when you make the numerical results, you obtain this. So here I have given n equal 200 and 1000. And so the horizontal axis is the log of sigma W. Vertical axis is the log of U4. And as you can see, you just fit perfectly. And as you can see, the fit or the numerical fit or we're matching the expectation from the theory. So it's really demonstrating that changing the standard deviation of your weight distribution is just a RG flow in the space of neural network. And again, to stress with respect to the question I had in the introduction, here it's a flow in the space of neural networks and not in the flow in the layers. Just small comments. So in fact, the active RG flow should have been expected from string field theory. So as you know, I like to work on string field theory also. So here, in fact, the standard deviation is like the stub parameter in string theory. And the ghost net is really like the p-adic string theory. So, okay, I don't want to go in the details, but it was studied already in string theory that changing the stub rates is like a Wilsonian RG flow, in particular by Ashoksen and other people before. And you can also add stubs in QFT. So this has been done quite recently, and there is some work to appear with Vincent Godet, who is at ICTS. And also the non-locality for this kind of field theory is studied in a paper to appear soon with Firat and Sviba. Okay, so let me conclude. So we made some additional checks of the neural network's QFT correspondence in our paper. Then we proposed a map of the possible theory space. So we're trying to explain what you should think when you write your action for this NN-QFT and not be too influenced by particle physics. We proposed passive and active RG flow equation for the neural networks. We proved that the change in standard deviation is the RG flow in the space of neural networks, and we made some numerical tests. So what we want to do later, so first, it would be nice to increase the number of dimensions and the order in the N expansion. It would be nice to investigate properly if non-locality and random tensor models are useful for this kind of QFT. It would be even more important to consider more general architectures and then to generalize the RG flow to non-translation invariant kernel. And then, as I was mentioning, we would like to find the proper numerical test for the passive RG flow. And I thank you for your attention.
Thank you, Harold, for this amazing talk. And so we already had many questions during the talk. So perhaps we should conclude with some very short questions for now. So please ask if you have some short questions. Yes, there is already a hand raised. Please ask, Ali Bodhi.
Yes. So basically, what I understand is that you are trying to translate the, the effective theories, as the neural network. So, what sort of experimental data you are using here to compare your simulated data?
So for the simulated data, we start by writing like a very large numbers of neural networks like this. So I will just take a very large number of different W0, W1, B0, B1. So we get a very large number of functions like this, which I will represent as a, it just function in Python, which is computing this matrix multiplication and applying the kernel. And then I will compute the correlation function like this. So you just take the product of each function applied to the different points, and then you average over all the neural networks you have set up. And this is giving you endpoint correlation function. So it's really what you would do with data. Like if you have a function of X and you want to find its correlation function, you would compute it in this way. So we are just doing this. And then we also want to compute this from Feynman diagrams.
And then from where you are taking the experimental data?
I have done them with Python. So I just wrote this function f as I was saying. So in Python I started to write. So I code this points. Then I'm having using some model to get Gaussian distributions from which I take this W and B, and then I just have a function which compute my f for all the possible samples I have taken from these distributions. So I computed numerically and.
Okay, and for the rectilinear units, is just the copy of the existing softwares, or you just reuse something that you have developed?
So here, for this very simple case, I just used NumPy, which is a standard package in Python. If we were doing training and so on, then yeah, we would use something. So the code for this paper is available on GitHub. So if you look in the paper, there is a link for the GitHub. So I didn't develop like any specific packages. We just some quite simple code. I know that in these papers I also have the code, and they use PyTorch for doing it. And in their second paper, because they are doing trainings, they also need with PyTorch and some specific package. But because here, okay, and I think they are using also data from MNIST, which is a handwritten digit recognition data set. So in this case, they also reuse some code. But the point that if you want to test a simple setup, you can just code everything yourself. It just like a few hundred lines of code. If you want to just do like more real data sets, then you will need to reuse some specific package.
Okay, and then for the temporal component, I mean, do you treat it differently, or it just, I mean, you just translate as the data point?
So here I'm working in a credence space, so I don't have time.
Okay.
Okay, so I think we already had quite a few questions. So maybe somebody else can ask some short question, or Kaushik, you have any?
No, I had a lot of questions already. So
okay.
Only request is for the reference. Harold said that he will send this reference. Yeah,
I'm looking for it right now.
You got yeah.
Okay, I mean, we can also have like a very short informal chat also after we close close the recording.
Yeah.
So if there is no further question, so let's.
Yeah, it was a very nice talk, Harold. Enjoyed it.
Thanks, Kaushik.
Yeah, and in fact, you should give another talk on string field theory.
That
when
would
you
be
want.
very nice. That would not be another talk. That will be a few other talks.
Okay.
Yeah.
Okay. Very good. Okay, so let me close the recording.
Yeah.